5.5 Calorimetry. Since we cannot know the exact enthalpy of the reactants and products, we measure the enthalpy change through calorimetry, the measurement of heat flow. Heat capacity and specific heat. The amount of energy required to raise the temperature of a substance by 1 Kelvin, or 1 degree Celsius, is its heat capacity. We can see several specific heat capacities in the table below. Notice that water has the highest specific heat capacity in the chart. This means that it requires a lot of energy to heat up a quantity of water compared to something like iron, which only has a specific heat capacity of 0.45 joules per gram Kelvin. We define specific heat capacity, or simply specific heat, as the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin degree. Specific heat then is equal to heat transferred divided by the mass times the temperature change. Relating heat, temperature change, and heat capacity. How much heat is needed to warm 250 grams of water from 22 degrees to near its boiling point, 98 degrees Celsius? The specific heat of water is 4.18 joules per gram Kelvin. What is the molar heat capacity of water? In Part A, we must find the quantity of heat needed to warm the water, given the mass of the water, its temperature change, and its specific heat. In Part B, we must calculate the molar heat capacity of water from its specific heat. Plan. For Part A, we are given C delta S, which is the specific heat, M stands for mass, and delta T, which is the change in temperature. We can calculate the quantity of heat, Q, using equation 5.22. We can use the molar mass of water and dimensional analysis to convert from heat capacity per gram to heat capacity per mole. The water undergoes a temperature change of 76 Kelvin. The initial temperature The final temperature is 98 degrees Celsius, and the initial temperature is 22 degrees Celsius. So our delta T is final minus initial, which gives us a temperature change of 76 degrees Celsius, which is the same change as 76 Kelvin, because 1 degree Celsius equals 1 degree Kelvin in magnitude. Using equation 522, we have that heat is equal to the specific heat times the mass times the temperature change. We're given the specific heat capacity of water in joules per gram Kelvin, 4.18. We multiply by the mass of the water sample, which was about a cup of water, or 250 grams, and then multiplied by the temperature change, which we calculated as 76 Kelvin. We then get 7.9 times 10 to the 4th joules. Part B, the molar heat capacity, is the heat capacity of 1 mole of a substance. Using the atomic weights of hydrogen and oxygen, we have that 1 mole of water equals 18.0 grams of water. And from the specific heat given in Part A, we have that the heat capacity, or molar heat capacity, is equal to 4.18 joules per gram Kelvin times 18 grams per mole, or 75.2 joules per mole Kelvin. For practice, please calculate. Large beds of rocks are used in some solar heated homes to store heat. Assume that the specific heat of the rocks is 0.82 joules per gram Kelvin, and calculate the quantity of heat absorbed by 50 kilograms of rocks in their temperature if their temperature increases by 12 degrees Celsius. Also, what temperature change would these rocks undergo if they emitted 450 kilojoules of heat? Constant pressure calorimetry. By carrying out a reaction in aqueous solution in a simple calorimeter such as this one, one can indirectly measure the heat change for the system by measuring the heat change for the water in the calorimeter. Because the specific heat for water is well known, 4.184 joules per gram Kelvin, we can measure the enthalpy change for the reaction with this equation. Heat equals mass times specific heat times delta T. Sample exercise 5.6. Measuring enthalpy change using a coffee cup calorimeter. When a student mixes 50 milliliters of 1 molar hydrochloric acid and 50 milliliters of 1 molar sodium hydroxide in a coffee cup calorimeter, the temperature of the resultant solution increases from 21 degrees Celsius to 27.5 degrees Celsius. Calculate the enthalpy change for the reaction in kilojoules per mole of HCl, assuming that the calorimeter loses only a negligible quantity of heat, that the total volume of the solution is 100 milliliters, and that its density is 1 gram per milliliter, since most of the solution is water-based, and also that its specific heat is 4.18 joules per gram Kelvin. Mixing solutions of hydrochloric acid and sodium hydroxide results in an acid-base reaction or neutralization reaction in which water and salt are formed. We need to calculate the heat produced per mole of hydrochloric acid, given the temperature increase of the solution, the moles of hydrochloric acid and sodium hydroxide involved, and the density and specific heat of the solution. The total heat produced can be calculated using equation 5.23. The number of moles of hydrochloric acid consumed in the reaction must be calculated from the volume and molarity of the substance, and this amount then used to determine the heat produced per mole of HCl. Because the total volume of the solution is 100 milliliters, its mass is 100 grams, since the density of water is 1 gram per milliliter. The temperature change is the final temperature minus the initial temperature, or 6.5 Kelvin. And using equation 523, we have that the heat of the reaction is equal to negative specific heat times mass times delta T. Our specific heat of water is 4.18 joules per gram Kelvin. Our mass was 100 grams of solution, and our temperature change 6.5 Kelvin. Because the process occurs at constant pressure, to express the enthalpy change on a molar basis, we use the fact that the number of moles of HCl is given by the product of the volume and concentration of the solution. So 0.05 liters times 1 mole per liter equals 0.05 moles. Thus, the enthalpy change per mole of HCl is delta H equals negative 2.7 kilojoules per 0.5 moles, or negative 54 kilojoules per mole. Delta H is negative, exothermic, which is expected for the reaction of an acid with a base and evidenced by the fact that the reaction causes the temperature of the solution to increase. The molar magnitude of the heat produced seems reasonable. Please complete the practice exercise. When 50 milliliters of 0.1 molar silver nitrate and 50 milliliters of 0.1 molar HCl are mixed in a constant pressure calorimeter, the temperature of the mixture increases from 22.30 degrees Celsius to 23.11 degrees Celsius. The temperature increase is caused by the following reaction. Silver nitrate reacts with hydrochloric acid, producing silver chloride, a precipitate, and nitric acid. Calculate the enthalpy change for this reaction in kilojoules per mole of silver nitrate, assuming that the combined solution has a mass of 100 grams and a specific heat capacity of 4.18 joules per gram degree Celsius. Bomb calorimetry. Reactions can be carried out in a sealed bomb, such as this one. The heat absorbed or released by the water is a very good approximation of the enthalpy change for the reaction. Because the volume of the bomb calorimeter is constant, what is measured is really the change in internal energy, delta E, not delta H. For most reactions, the difference is very small. Measuring the heat of reaction using a bomb calorimeter. Methyl hydrazine is used as a liquid rocket fuel. The combustion of methyl hydrazine with oxygen produces nitrogen gas, oxygen gas, carbon dioxide gas, and water liquid. When 4 grams of methyl hydrazine is combusted in a bomb calorimeter, the temperature of the calorimeter increases from 25 degrees Celsius to 39.50 degrees Celsius. In a separate experiment, the heat capacity of the calorimeter is measured to be 7.794 kilojoules per degree Celsius. Calculate the heat of reaction for the combustion of a mole of methyl hydrazine. We are given a temperature change and the total heat capacity of the calorimeter. We are also given the amount of reactant combusted. Our goal is to calculate the enthalpy change per mole for a combustion of a reactant. We will first calculate the heat involved for the combustion of the 4-gram sample. We will then convert this heat to molar quantity. For combustion of the 4-gram sample of methyl hydrazine, the temperature change of the calorimeter is 14.50 degrees Celsius. Again, delta T equals T final minus T initial. We can use the temperature change and the value of the heat capacity of the calorimeter to calculate the heat of reaction. So we have that the heat of the reaction is equal to the negative heat capacity of the calorimeter times delta T. Our heat capacity of the calorimeter was measured to be 7.794 kilojoules per degree Celsius, and our temperature change was just calculated as 14.50, and that means that the heat of the reaction is negative 113 kilojoules. We can readily convert this value to the heat of reaction for 1 mole of methyl hydrazine. So we have negative 113 kilojoules per 4 grams of methyl hydrazine, which was our sample in the problem. We can multiply by a conversion factor, which converts grams to moles for methyl hydrazine using its molecular weight, which is 46.1. And then we wind up with a unit of kilojoules per mole of methyl hydrazine, negative 1.30 times 10 to the third. The units cancel properly, and the sign of the answer is negative, as it should be for an exothermic reaction. For practice, a 0.5865 gram sample of lactic acid is burned in a calorimeter whose heat capacity is 4.812 kilojoules per degree Celsius. The temperature increases from 23.10 degrees Celsius to 24.95 degrees Celsius. Calculate the heat of combustion of lactic acid per gram and per mole.